Hello friends, today we will start with a new module that is on severe plastic deformation. In the first few lectures we discussed about some non-conventional deformation, thermomechanical deformation processes nowadays which are coming up, okay, and the category in which they are put are called severe plastic deformation. Okay, so as the name suggests, the amount of deformation or amount of strain which you can put in the material is very high as compared to our conventional thermomechanical processing like rolling, forging, extrusion and so on. Okay. So, the idea of deformation itself is different than what we do in case of conventional thermomechanical processing. There the primary strain is compression. Okay. So, basically all the conventional thermomechanical processing is based on the compression of the sample, or they want to impose a strain in form of compressive strain. Okay. We do not do any thermomechanical processing using tensile strain. Okay. The reason is simple, that when you apply tensile stresses, okay, if any defect is there, it is going to open up. If you remember your basic fracture mechanics idea, okay, whereas if you compress the sample, okay, you close the defect. So, compression is the primary mechanism of deformation in conventional thermomechanical processing. In severe plastic deformation, the primary deformation mechanism is through shear process. Okay. And because you are in shear mode, okay, you are able to apply much larger strain as compared to in compression, because whenever you have compression you also induce some tensile stresses and some cracking will takes place if you apply very large strain. Okay. But in shear you are able to apply very large strain without inducing any defect in the material, defect in the form of cracking and so on. Other defects which are based on deformation processes like shear bands and flow localization may occur if you are doing at very high strain rates. Okay. So, in this category, the first one to what we are going to discuss today is called equal channel angular pressing. It is one of the most popular technique to impose very high deformation. Okay. One of the first one to start when people started talking about severe plastic deformation. Okay. So, the process is very simple, all these processes are actually very simple. Okay. So, in equal channel angular pressing, okay, basically you as the name suggests, you have there are two channels and these two channels are equal channel and there is a angle to this channel. Okay. So, if you see this diagram here, okay, so this is my sample, okay, this is the plunger with which you are pressing the sample, and if you see the die, okay, the die consists of this channel here, okay, through which the sample is going to go, and this cross sectional area of the channel and this cross sectional area of the channel, okay, both are same. Okay. So, that is why they are equal, and then there is an angle in the channel. Okay. So, when the material goes and take a turn here, okay, you are imposing a very high amount of shear deformation in the material. Okay. And the deformation shear deformation is in form of simple shear. Okay. So, you have intense plastic deformation in form of simple shear, and all these severe plastic deformation processes are usually used to produce ultra fine grain materials, okay, what we also called as UFG, okay, ultra fine grain. And in ultra fine grain also there are two approaches, from down to up, okay, and another is from top to down. So, this is a top to down approach where you have coarse grain material, okay, relatively in bulk, okay, and then you are deforming it and refining the microstructure. So, it is going from coarse to fine. Okay. And as I told you that E-cap die contains two channels, okay, equal in cross section intersecting an angle near the center of the die. Okay. So, this is the a very simple approach to the deformation process. Okay. If we want to look at the principle of the shearing process, okay. So, if you look in the diagram, so we are deforming the sample from the top, okay, and one element is taken here which is called 1 here before the deformation, okay, and this is my shear plane basically. So, and the element 2 is taken as after the deformation. Okay. So, if you see the element 1, okay, which is shown as a rectangle plane here, okay, and because of when it is going through this angle here, okay, what you are doing is you are applying a simple shear here, okay, which is shown with these 2 arrows. And when you look at the element 2, now the element 2 is deformed. Okay. So, now it has not remained a rectangle, it has become a parallelogram, okay, with a 45-degree angle here. Okay. So, the deformation here has taken this edge in front and this edge in the back, that is how the deformation is taking place, and because of that you have simple shear in the material. Okay. So, that is a very simple process like this, okay, that how you can apply a shear strain in the material. Now, the complexities will start coming in. Okay. So, we have to define a few parameters for the die here. Okay. So, for example, the die is shown here and there are 2 angles are shown here, one is angle phi and another is angle psi. Okay. So, the phi angle is basically the intersection of the 2 channels. So, when where the 2 channels are meeting, okay, if they are meeting at 90 degree, okay, then of course, the angle will be phi angle will be 90 degree, or it can meet at some other angle, okay, like this, or it can meet an angle like this. Okay. So, these are bigger angle more than 90 degree. Okay. So, this angle phi will be more than 90 degree, whereas this angle phi will be less than 90 degree. Okay. And this is my 90 degree. So, this is the intersection of the 2 channel, that how they are intersecting at 90 degree, more than 90 degree or less than 90 degree. The other angle is kind of how you are giving a curvature to the whole deformation process. Okay. So, you can have a very sharp curvature like this. Okay. Okay. But you can understand that material is a solid material, it is not a fluid, okay, which can occupy all the spaces available to it. Okay. So, when you are deforming, the material will not touch the very sharp edge of the die, okay, it will deform something like this. Okay. So, what kind of curvature we are providing, okay, to have a smooth deformation for the material. Okay. So, psi is the angle subtended by the arc of curvature at the point of intersection. Okay. So, at the point of intersection, what is this angle psi, okay, and what is this basically this curvature, and what is the angle of this curvature at the intersection point, okay, that defines the angle psi. So, these are the 2 important parameters of die design, that what should be the angle phi and angle psi. Okay. And basically the amount of strain which we are going to put in, okay, depends on these 2 angles, okay, with an equation as shown here. Okay. So, both angle phi and psi are coming in the expression, okay, and similarly the n is basically the number of passes. So, if you keep doing, so this is a equal channel as you can understand. So, I can keep putting strain in the material, and it is there is not going to be any change in the cross sectional area. So, there is no limit to the amount of strain I can put in the material, whereas if you do any rolling, extrusion or these kind of processes, as you keep putting strain in the material, for example, if you are doing rolling, the thickness of the material will keep reducing, and after a certain point, okay, it is not possible to put a strain in the material. Okay. So, if we look at the our conventional thermomechanical processes like rolling, extrusion and so on, when you put the strain, their cross sectional area reduces. For example, if you take rolling, okay, when we put the strain, the thickness of the material keep reducing, and after a certain point you won't be able to apply any strain because the thickness has reduced to such an extent. By having a equal channel here, I can put any amount of strain in the material, okay, by continuously taking through the die, okay, and that represent the number of passes here. So, what is the effect of angle phi and psi? Okay. So, in terms of strain, for example, this is the strain measured by doing some grid methods, okay, and the channel angle is on the x axis, okay, the phi, and different curves are shown here for different psi angle, okay. So, from 0 degree to 90 degree here, okay. So, you can see that for a very sharp angle, that is psi 0, okay, and at very low phi angle 60 degree means the phi angle will be something like this is 60 degree, okay. So, it is a very extreme amount of strain you are putting if your die is like this, okay, something like this, okay. So, the amount of strain is very high in this case, okay, and the n is only 1, that is only a single pass. So, in the single pass I can put in the strain of around 2.6 or 2.7, okay, very high strain. So, when you have a very sharp angle, okay, and psi is also 0 degree, the strain is very high. For the same 60 degree angle, okay, 60 degree or I think 50 degree here, if I reduce the psi, that means I start providing it a curvature, okay, the amount of strain goes from around 2.7 to around 1.4. So, a substantial reduction in the strain level, okay, just by changing the angle psi here, okay. Usually we do not use these kind of angle phi, okay, which are lower than 90 degree, because it will impose very high amount of strain in the material, okay, and which can give rise to defects, okay. Usually if you see the phi angle in the literature, it is either 90 degree or more than 90 degree, okay. So, if you go beyond 90 degree, the effect of angle psi actually start reducing, okay. In fact, for very high angle like 120 degree and so on, there is no effect of psi, okay. So, usually in the literature whatever you will find, the angle phi is more than 90 degree. So, there the angle psi angle has not much influence on the strain values, okay. And if it has a no effect on the strain value, then of course, it will not have any much effect on the microstructure also, okay. So, there are 4 microstructures are also shown here for phi angle more than 90 degree. So, 90 degree, 112, 135 and 157 degree here, okay. So, 90 degree is the one where you will have more strain, as you can see from the figure, okay. Whereas, for 157 degree the strain values will be much lower, which are in the range of what you get in conventional thermomechanical processing. So, around 0.3, okay, whereas in case of 90 degree it is around 1 or more than that, okay. So, the effect of strain you can see on the microstructure, that when you have 90 degree the strain is close to 1 here, okay. I can see very nice recrystallized microstructure and very fine microstructure, okay. As you can see, the scale is 2 micron and the grains within that is much finer than that. So, grain size must be around 1 micron or less than 1 micron, okay. Whereas, if you keep increasing the angle, here you do not see any recrystallized microstructure as such, okay. The grains are still coarse, okay, and also they have lot of dislocation density present in the material, okay. That means, it has not undergone the recrystallization process, or the recovery process is not very effective, okay. So, you can see effect of the die design on the microstructure, okay, for the same amount of strain, that if I have a sharper or smaller phi angle, okay, I would be able to impose higher strain, and that will be seen in the microstructure. Okay. Now, there are different variants to the how we are going to do the friction to how we are going to do the ECAP process. Okay. For because I can change the direction of the shear strain. Okay. So, if I start with let us say some ingot here, okay, and let us say I can give them some name here, for example, let us call this as A, B, C and D. Okay. Now, suppose as you can see in root A, okay, suppose this is my top the plane is A and the bottom plane is of course, it will be C then, okay, and I am doing one deformation. So, A will be on top, C will be on bottom, and again I am putting in the same configuration that A, when it is going to come out, A will be on top and C will be in the bottom, then this will be a root A. Okay. So, I am not changing the direction of the shear, okay, I am repeatedly doing in one way. Okay. If you see this root B A, A is in subscript here. Okay. In this case, what you are doing is that you are alternating between the two different planes. Okay. So, for example, in first case, if it is A here and here it is C, okay, when you put it back, okay, then and when it is coming out here, then the B will be on top, okay, and of course, then D will be in the bottom. Okay. And again, when you put the next time, A will come on top and B will come C will come in bottom. Okay. So, it is kind of alternating between this position and and again coming back to this position. Okay. So, the arrow shows that you are again coming back to the first configuration. Then you have a root BC. Okay. In this case, you are continuously changing the position of, if this is my first plane, which is the A plane here. Okay. So, now it goes here, then it goes here, then it becomes here and again comes back to A. So, there is a continuous rotation here. Okay. So, A C here, then when it is coming out, it is B D, then next cycle again it becomes I think C A, and then next cycle it becomes D B, and then another cycle it again becomes A C. Okay. So, it starts from A C, then become B D and so on. Okay. So, continuously you are changing the position. So, every time the shear plane direction is changing. Okay. Then you have a root C, okay, in which case you suppose if this is your A plane and this is your C plane, okay, then next cycle it will be C above and A below. Okay. So, it is like 180-degree rotation you are doing. So, one configuration like this and next configuration is directly like this. So, shear plane is getting 180-degree rotation every time. Okay. And obviously, when you are doing this kind of variations, it is going to change the microstructure which is going to be generated, because your shear plane is continuously changing. Okay. So, there is a large amount of work on these variations also, that what is the effect of, see, amount of strain will be same now. Okay. So, the only change will come because of the change in the shear plane. Okay. And there is large amount of work on that, how what will be the effect of these roots on the microstructure. Okay. Now, what are the effect of passes, for example? Okay. So, you have one microstructure, nice microstructures are shown in 3 dimensions, as you can see. Okay. So, just to give you the idea about x, y and z, I will go back to a previous slide. Okay. So, this is what x, y, z is. Okay. So, x is this plane, y is this plane and z is this plane, okay, the top one. So, the shearing is taking place in this y plane, okay, like this. So, this is what you can see in the y plane, because of the shearing the grains are elongated, okay, and also they are at a certain angle, okay, which will be defined by the shear angle of the shear plane. Okay. The in the Z plane, if you see, all the grains are looking only as a kind of compressed, okay, more or less equiaxed and compressed kind of. In the X plane, you can see the elongated grains in this direction, okay, because there you see the shearing taking place in Y plane. So, these grains are getting elongated in the in this way, okay. So, but the important is this particular Y plane where because of shearing you have grains, okay, aligned in the direction of the shear plane, okay. Now, what will be the effect of passes using these roots? So, we are using root BC. So, in root BC you are rotating the plane every time. So, it is all the rotations are given to the plane. So, in 4 passes actually you have complete the whole cycle of deformation. So, shear plane has changed every time and it has completed the whole 360-degree rotation, okay. So, if you do that, you can see the difference between the two microstructure, okay. Here the microstructure, the grains are very coarse, you can see the scale here 500 micron, okay. So, very big grains, elongated grains, okay, and aligned in the deformation direction, whereas if you see after 4 passes, okay, the grain size has refined and the scale you can see it is 2 micron here, okay, and more or less the grains are in that range, okay. So, it should be even less than 1 micron, okay, and in all the 3 planes the microstructure is looking uniform, okay. So, that is a very good way to, if you want a uniform microstructure, okay, if I follow this root BC, I should be able to get in 4 passes a very uniform ultra fine grain microstructure, okay. So, from 500 like maybe like the grains must be around 100 to 200 micron, you have reduced it to 2 micron, order of magnitude difference in the grain size, okay. Now, this is the effect of pressing speed. So, how fast I am pressing it, okay, that also will be a variable, okay, but in the literature we do not see much effect of the pressing speed on the, for example, yield stress here, okay. Microstructure will of course get refined, okay. So, these are the number of passes, the circle, open circle is first pass and the inverted triangle is the 4th pass. So, obviously, as you increase the number of passes is increasing in this direction, my yield strength is increasing because I am refining the microstructure, okay. So, from around 200 megapascal it is going up to 260 or 70 megapascal. However, there is not much change because of the ram speed, okay, how fast I am forcing it to deform, okay, and you can see that there is a order of magnitude difference between the strain rate or the ram speed which is in millimeter per second here from 10 to the power minus 2 to 10 to the power 1, okay. So, a large difference in the ram speed. So, strain rate will be quite different in each of these cases, but there is not much effect on the yield strength of the material because of that, okay. So, mainly the strain is the more important parameter here for altering the properties of the material through ECAP process, okay. Effect of pressing temperature, okay, that at what temperature I am doing the deformation, okay. So, if you see that again this is ECAP temperature in Kelvin and there is a grain size, okay, and this data is for aluminum, magnesium alloys, and in one case scandium is also there, okay. So, of course, there is as the temperature is changing from 300 to 600 Kelvin. So, roughly around let us say up to 300 degree Celsius they are going. And the grain size is less than 1 micron in case of scandium containing alloy, okay. For pure aluminum the grain size is ranging from 1 micron to around 4 or 5 micron, okay. So, huge reduction in the grain size through ECAP process, okay, and also the effect of temperature can be seen. If temperature is more, already we know that when temperature of deformation is high, okay, your grain size which you achieve after the deformation process is going to be high. Okay. So, this is the effect of temperature on the grain size. Another effect we already know about is what we call as adiabatic temperature rise, okay. That is when you deform a material, okay, because of the deformation. Already we have seen in case of processing maps that when you put in any power, okay, in terms of like we are going to deform the material here, okay, some will be going into microstructural change and some will be going in heating the material. So, this is the adiabatic temperature rise as a function of deformation, okay, and pressing speed is given as 18 mm per second here, okay, and the ambient temperature is around 11 degrees Celsius. So, the adiabatic temperature rise in pure aluminum is around 30 degrees Celsius, okay. So, from 11 to it is going up to 40, and in different passes there is not much difference in the rise in the temperature, okay. So, it is a very consistent process in that way. In another alloy where you have 3 weight percent magnesium, okay, again pressing speed is same, okay. Again you can see now the temperature rise is around 80 degrees Celsius from 11 or 13 in this case to around 90, okay. So, around 80 degrees Celsius temperature rise is there, okay. So, delta T here is around I would say 30 degrees Celsius and delta T here is around 80 degrees Celsius, okay. So, with the same pressing speed, this is important here, okay, you are able to achieve more temperature in case of a material which has some alloying element, okay. So, we expect that when you have alloying element the strength of material will be high, okay. So, the temperature rise in case of ECAP depend on the strength of the material as well as ram speed, okay. So, as you increase the ram speed also there will be effect on the temperature rise, okay. So, ram speed is not affecting that much the yield strength, but when you are deforming the material due to temperature rise it may affect slightly the microstructure of the material, okay. So, now all these things ultimately when you do anything like this processing to change the microstructure and so on, basically we ultimately do it to get some property, okay. So, all this ultra fine grained material or production of ultra grain fine material started with the Hall-Page relationship, which says that if you keep reducing the grain size the strength of material will increase, the yield strength let us say of the material will keep increasing, okay, as a function of d to the power minus half, okay, that we know from Hall-Page relationship. So, the ultra fine grained material production of ultra fine grained material started from the Hall-Page relationship that let us increase the strength of material just by reducing the grain size, okay. So, what is the effect of all this ECAP process on strength and ductility that is shown here in this graph, okay. So, on the x axis you have equivalent strain, okay, and y axis you have elongation to failure, okay. So, equivalent strain means already we have seen the relationship for the strain. So, that is the amount of strain which you are putting in the material, and after putting different amount of strain, okay, the strength of the material is noted down, okay. The dotted circle here gives the strength after the rolling, okay. So, in rolling you can achieve maybe the maximum strain of around 2.2 or so, okay, 2.2 or 2.4, whereas in case of ECAP you can go up to strain of 8 in this case, in fact you can go more also. So, what is the effect of this imposition of strain, okay. So, the elongation the yield strength is on the other side, okay. So, yield strength is increasing from 100 megapascal, okay, to around 380 megapascal. So, big jump in the strength of the material by doing by imposing the strength through ECAP process. Okay. Whereas, if you see the ductility, ductility reduces substantially. So, okay, initial material the ductility was around 31%, okay, and that got reduced to somewhere around 14%. So, almost half the ductility, okay, but the strength is more than 3 times. So, this kind of balance between strength and ductility is always there whenever you want to produce ultra fine grained materials, okay, that although the strength increases following the Hall-Page relationship, but the ductility of the material reduces. Okay. And the reason for that is that when the plastic deformation is through generation and movement of dislocations, if you keep reducing the size, okay, the generation of dislocation becomes that much difficult, okay, and then the dislocation as a deformation mechanism will not be an effective mechanism as you reduce the grain size. Okay. So, when it does not become a important mechanism, then the problem comes that what will carry the deformation process. Okay. So, if there is no other alternative deformation mechanism, then the ductility of the material will come down. So, though the strength is more, because you now require much higher stresses to generate dislocation or move dislocation because of the reduction in grain size, the ductility will reduce. Okay. So, there are now people have tried ways to improve the ductility, okay, without compromising the strength. Okay. So, there are couple of approaches there. So, the first approach is that do not stop grain refinement up to a certain level, you keep reducing the grain size to even more smaller sizes, okay, and with very high fraction of a high angle grain boundary. Okay. So, have a fine grain size with very high fraction of high angle grain boundaries. If you do that, then the deformation mechanism change from dislocation based to grain boundary sliding. Okay. If you remember, grain boundary sliding we discussed when we were discussing about the creep deformations. Okay. So, in creep and especially in superplasticity, the grain boundary sliding is a very important deformation mechanism. As I told you that deformation will not be through dislocation movement within the grain, but the grain itself will have a rigid body or there will be a grain boundary sliding. Okay. So, grain 1 and grain 2 will have a movement relative to each other without having any dislocation movement inside the grain. Okay. Some dislocation movement can be there to accommodate the stress concentration, but mainly the deformation will be through grain boundary sliding. So, if dislocation is not effective when you have fine grain material, so you can look for some alternate deformation mechanism by designing the microstructure, okay, and that can be grain boundary sliding. Okay. And in grain boundary sliding the ductility can be very high, which is possible in superplastic material also. The second approach is to have bimodal grain size arrangement distribution. So, you can have fine grain as well as some few coarse grains. Okay. Some proportion of fine and coarse grain can be there. Okay. And this combination of fine and coarse grain, okay, will give you the required strength and ductility. Okay. So, the finer grain will provide you the strength, okay, whereas the coarser grain will provide you the stability during the deformation through dislocation movement. Okay. So, this is another approach to have to compensate for the reduction in ductility. So, both the strength and ductility will be high, okay, when you have bimodal grain size distribution. Okay. So, these are the few basic ideas about equal channel angular pressing. Of course, this is not a very exhaustive lecture, okay, but if you are interested, a lot of literature is available, okay, and you can start working on that. Okay. So, with that I will close this particular lecture on ECAP, Okay. So, thank you for your attention.